This is the 9th video for paper 3 of the higher paper. Now, to start off with, this question looks a lot like one that we've done on paper 2. In fact, this question was revised for paper 2 when we were looking for the area underneath the graph. For a speed-time graph, the area underneath represents distance. Here, we are going to ignore part A and look at part B instead. So this question is asking us to find the gradient at 70 seconds. What that represents is the acceleration. In this case, the acceleration of a snowboarder, and we are looking for that at 70 seconds. So the way we do that is if we go to the graph to 70 seconds, start off by finding the point on the curve that shows 70 seconds. What I then do is take my ruler and I need to draw a straight line that follows the steepness of that curved section. So obviously I'm not going to do it like this because it's crossing into the graph. What I need to do is almost try and place a straight line on so that it just touches the graph. You can draw this as long as you want, but to have a bit of a longer line will probably help when we try and pick out some relevant points in a second. What we then need to do is find this line's gradient. To do that, what I'm going to do is pick off a point that I can read quite easily. So I'm going to pick this point here, and I'm also going to pick this one here, and I'm going to draw a little triangle, just like we would do if we were finding the gradient of a linear graph. So to find the gradient of this line now, I need to know the change in y, so the length of this part here, and the change in x, so the length of this part here. Well, if we look, this section goes from 10 down to 6, so the length of that line is 4, just going from 6 up to 10. And for the x value, we have got that it goes from 52 down here up to 90. So the difference there being 38. So in order to find the gradient, all we do is the change in y divided by the change in x, which in this example would give us 4 over 38, or alternatively 2 over 19. You're fine to leave it as a fraction, or if you wanted to use your calculator, you could work out an exact decimal. The next topic we're looking at is invariant points. Now, an invariant point often comes on a transformation question. An invariant point is simply one that does not move when you perform the transformation. We're going to look at 3 different types of transformation here, all using the exact same starting point. So for the first one, we're looking at translation. If I translate this square using the vector 3, 1, what I would get is that each corner would move to the right 3 and up 1, therefore placing the square there. So if we look, there are no points on this square that have not moved. All the points of the square have moved, so we would say that there are 0 invariant points, because an invariant point is one that does not move during the transformation. The next part, we're using the exact same shape again, but this time we're saying that we are enlarging this shape by a scale factor 2, using a centre of 0, 0. What that means is that this point here is fixed, that's not going to move, and we are stretching our square out, so we are doubling the size of it. So if it stretches out, it would mean our square would now be twice as big, or each length would be twice as big, but the centre of enlargement would not move. So the only point that has not changed, obviously this point is now up here, this corner is now up here, and this one is now over here. The only point that's not moved is this one down here. So we have got one invariant point. The third and final one that we are looking at is a reflection. So we are going to reflect the shape OABC, so our little square that we started with, in the line y equals x. Well, the line y equals x is the point where all x and y coordinates are equal, so that would be this line here. If I reflected it in that line, the square would not actually look like it's changed. It would still look like this, but this corner has moved down here, this one up here, but the 2 points, the 2 corners of our square that are on the mirror line have not moved. So for this, the reflection, this point has remained invariant, as has this point here. So we would say for this one that there are 2 invariant points.